What's the value in measuring the quality of our air? Countries around the world have been monitoring air quality for decades in order to protect the health and well-being of their citizens. Grenada is a beautiful country with wonderful people, delicious food, and water as blue as can be. However, up until the year 2020, Grenada did not have a systematic outdoor air pollution monitoring program. While at first glance there may not seem much to worry about, Grenada along with other Caribbean islands are subjected to seasonal desert dust storms that originate from the Saharan and Sahel desert regions of North Africa. With the help of an air quality monitoring system, it's possible to more precisely quantify the impact of air pollution on the air that we breathe. Over the last two videos, I've introduced my air pollution research projects taking place in Grenada, and I've shown you how I did it. But now it's time to present exactly what I found and break down what it all means. So with that being said, let's get into it. With the help of my superiors from Carleton University, Dalhousie University, and St. George's University, I was able to collect ambient PM2.5 concentration data from January 6th to December 31st, 2020. Using these data, I calculated the daily mean and produced the line charts for the duration of the study period. On the left, I have a line chart displaying the daily mean PM2.5 values averaged across the 5 monitor locations for 2020, and on the right, another line chart showing the daily mean PM2.5 values for each of the 5 monitor locations during the same study period. In general, I found great synchronicity in the measured daily mean PM2.5 values taken across the 5 monitor locations on Grenada and Curacao. This held true for the majority of the study period, regardless of which monitors were installed at that particular time. I also calculated basic descriptive statistics to provide a more in-depth look at the daily mean PM2.5 values measured at each monitor location and the average of all 5 together. Included in these statistics are the minimum, first quartile, third quartile, and maximum daily mean PM2.5 values. Next, I'd like to point out that the mean daily mean that I calculated, average across all monitors for the duration of the study period, was 4.4 micrograms per meter cubed. This is less than the recently updated World Health Organization annual mean guideline value of 5 micrograms per meter cubed for PM2.5. The mean daily mean value that I found in Grenada was low relative to other countries. This is exemplified by the findings in the 2020 edition of the World Air Quality Report, where the annual mean PM2.5 concentration was found to be highest in Bangladesh at 77.1 micrograms per meter cubed. Meanwhile, the corresponding values for the US and Canada were 9.6 and 7.3 micrograms per meter cubed, respectively. In a more regional comparison, the mean daily mean that I found in this project was similar to those found at fellow Caribbean nations, the US Virgin Islands and Puerto Rico. The annual mean PM2.5 concentration that was found at each of these locations in 2020 was 3.7 micrograms per meter cubed. Another point I want to make note of here is that there are 5 days where the average daily mean PM2.5 concentration in Grenada exceeded 15 micrograms per meter cubed. This benchmark is relevant because it is the WHO's 24-hour mean guideline value for PM2.5. I also identified Saharan Dust episodes to have occurred on each of these 5 days in Grenada. Combining these two observations, it appears similar to findings from other island setting studies that found Saharan dust intrusions to be responsible for large increases in ambient PM2.5. However, a key difference in what I found versus these other island setting studies is that the ambient PM2.5 concentrations on Saharan dust days were generally higher at these other islands relative to Grenada. It's possible that these differences are partially explained by Grenada generally having lower background concentrations. Some factors that could contribute to this include 1. The rugged topography of the islands and the consistent airflow from trade winds, as both factors may play an important role in the dispersing of particulate matter on the island of Grenada. Somewhat separate to this island setting comparison, Grenada is unlike other countries in the Northern Hemisphere, due to the absence of temperature inversion effects that can cause higher pollution levels during the winter season. 3. Since Grenada has consistently warm temperatures throughout the year, the island does not have sources of air pollution that result from the heating of homes. And 4th, another possibility is that purple air monitors used in this study may have actually underestimated ambient concentrations of PM2.5 when exposed to Saharan dust. It has been demonstrated in laboratory and outdoor environments that plant towers sensor PM2.5 readings underestimate actual PM2.5 concentrations when exposed to dusts. Further, it's possible that the laser channel-based sensor readings are affected by variations in dust particle shape, color, composition, and surface area. This may be related to the assumptions made about particle diameter, density, and shape by the plant tower sensors. Another hypothesis stated in Cosmopoulos et al. 2020 is that high levels of quartz particles, such as during a Saharan dust storm, lead to a different behavior of the purple air sensors for the measurement of particulate matter of varying sizes. Now, if you want some more information on this topic, I highly recommend checking out this post by Guo Lavar titled Thoughts on Low-Cost Air Quality Sensors, that can be found on the publiclab.com website, where the author discusses the use of purple air monitors and how they relate to higher quality monitoring devices. Now, let's shift perspective and take a look at the monthly changes of PM 2.5. Using the daily mean values that I calculated throughout the study period, I created box plots to demonstrate how PM 2.5 varied from month to month. In a simple sense, box plots display how the values in your dataset are distributed by providing visual representations of key statistics, such as first quartile, median, and third quartile. Accounting for data collected between January and December 2020, monthly mean PM 2.5 concentrations in Grenada ranged from 2.9 to 8.1 micrograms per meter cubed. Aside from periods in which Saharan dust episodes impacted Grenada air quality, most months had low levels of ambient PM 2.5. Months with the highest average monthly PM 2.5 concentrations, February and June, were influenced by Saharan dust episodes, as there were 15 and 12 Saharan dust days identified during these 2 months, respectively. Taken together, these data patterns suggest that the Saharan dust is a dominant source of PM 2.5 exposure in Grenada. In an effort to contextualize these monthly PM 2.5 values in Grenada, I scoured the literature and found this really cool historical construction of the annual cycle of dust mass concentration in Barbados, based off data collected from 1973 to 2017. The annual cycle of dust mass concentrations in Barbados shows that there is a clear season of maximum dust transport to the southern Caribbean region from May to September. The month with the highest monthly mean dust mass concentration in Barbados is June. This parallels June having the second highest monthly mean PM 2.5 concentration measured in Grenada, largely driven by frequent Saharan dust episodes. However, February had the highest monthly mean PM 2.5 concentration in Grenada, here attributed to Saharan dust episodes as well. At first glance, this appears to be an anomaly that does not align with the annual cycle of dust transport to Barbados. Though, interestingly, the past decade in Barbados has been characterized by greater year-to-year variability in dust concentrations measured during spring and summer seasons than in years past. Thus, the February 2020 peaks in daily mean PM 2.5, measured in my study, may be part of a trend of greater year-to-year variability in Saharan dust emission and transport. Next, let's delve into the day-of-week changes in ambient PM 2.5. On a day-of-week basis, no statistically significant differences in the daily median concentrations of PM 2.5 were found. The median PM 2.5 concentrations range from a low of 3.2 micrograms per meter cubed on Tuesdays to a high of 4.0 micrograms per meter cubed on Thursdays. On a time-of-day basis, when only considering data collected during weekdays, the differences in ambient concentrations of PM 2.5 were negligible when comparing urban and rural monitoring locations in Grenada. For this urban versus rural comparison, the mean concentration at the urban location was 5.0 micrograms per meter cubed, while for the rural location it was 5.2. The largest difference in exposure occurred between 10 p.m. and 6 a.m., where the mean concentrations in urban and rural locations were 4.7 and 5.2 micrograms per meter cubed, respectively. Ambient PM 2.5 concentrations were similar in urban and rural locations throughout the day, despite there being differences in housing density and nearby road traffic between the two locations. This suggests that due to the small size and similar topography across the island, there's little spatial variation in ambient concentrations of PM 2.5 in Grenada. This also suggests that regional and not local sources of air pollution are a key driver of excess ambient concentrations of PM 2.5 in Grenada. It is possible that there exist spatial variations in other concentrations of traffic-related pollutants, such as NO2 and ultrafine particles, on the island. Given the role these pollutants also have on human health, further exposure studies that explore these variations should be considered. I posit that the largest difference in PM 2.5 found during this time-of-day comparison may be due to the diurnal cycle of sea/land breezes. As documented in another island-setting study, breezes from the sea come inland during the daylight hours and air masses from inland flow towards the sea at night. At a coastal background site on the islands, a smooth increase in PM1, PM2.5, and PM10 was observed during nighttime hours. And this was associated with winds transporting air masses from the city center of Santa Cruz de Tenerife toward the sea. Next up, let's discuss the associations between daily measures of PM2.5 and daily meteorological measures. I conducted Pearson correlation tests to estimate the strength of a linear relationship between daily meteorological measures and PM2.5 concentrations. The strongest correlations were observed between the daily mean PM2.5 variable and visibility, wind speed, and atmospheric pressure. Of the meteorological measurement studies, daily mean visibility had the strongest linear relationship to ambient PM2.5. To me, this is not surprising given that generally, reductions in visibility are accompanied by the presence of ambient PM2.5 due to its light scattering and light absorption capabilities. In addition to visibility, wind speed was modestly positively associated with PM2.5. As noted in the ambient particulate matter study done in Trinidad and Tobago, a positive association between PM2.5 and wind speed may be due to increased transboundary pollution. Previous research has also shown that dust storms are often accompanied by higher wind speeds. Similarly, the wind speeds observed in Grenada were higher on Saharan Dust days as opposed to non-dust days. Finally, I want to briefly comment on the weak association that I found between daily atmospheric pressure and PM2.5. In general, low-pressure weather systems bring wet and windy conditions that wash out the pollutants from the local air and transport them to a new area. In contrast, high-pressure weather systems create stagnant air conditions that allow for emitted pollution to concentrate in a local area. Thus, this finding appears to follow the usual relationship between these two variables. During my study period, I identified 56 days that were adversely impacted by Saharan dust, and 310 that were not. The mean daily PM2.5 concentration on these Saharan dust days was 8.5 micrograms per meter cubed, which was 2.5 times higher than on non-Saharan dust days. Daily concentrations of PM2.5 in Grenada peaked during the Godzilla Saharan dust storm that occurred between June 21st and 23rd, 2020. Aside from these dust episodes, daily ambient PM2.5 in Grenada is fairly low, likely due to the relatively small population, lack of major industrialization and motor vehicle traffic on the island, as well as consistent airflow from the trade winds that disperses particulate pollution. In addition, unlike other countries in the northern hemisphere that have higher pollution levels in the winter, Grenada has relatively constant warmer temperatures, and thus does not have sources of air pollution from the heating of homes. About a year after I finished my master's degree, I did some additional research assistant work with my thesis supervisor. The objective of this work was to record all days when a Saharan desert dust storm occurred in Grenada from 2000 to 2022. However, since there was a limited availability of meteorological data, the best that I could do was identify the Saharan dust days from January 1st, 2005 to November 31st, 2022. When I worked on my master's thesis, I was time constrained to cobble together a method to identify when Saharan dust days occurred in Grenada in 2020. It wasn't perfect, but I got the job done. Fortunately, for this research assistant work, I had more time to try and come up with a better method, and I think I accomplished that. My updated method used two data sources. One, NASA's MERA-2 atmospheric reanalysis dust surface concentration data, and two, daily mean visibility data that I obtained from the Meteorological Office at Grenada's Maurice Bishop International Airport. When it comes to MERA-2, you can think of it as a calculation of aerosol values across Earth, using a combination of forecast model data, ground level observation data, and satellite observation data, where the forecast model values that MERA-2 uses are constrained by observation data. This is why it's important to state that these MERA-2 derived aerosol concentration values are considered observation-based data and not observational data. MERA-2 uses this combination of forecast model data and observation data to create a gridded dataset across Earth for a broad range of variables such as surface level concentrations of black carbon, organic carbon, dust mass, sulfates, and sea salt mass. The grid cell that entirely contains the island of Grenada is the grid cell that I chose to download this MERA-2 dust surface mass concentration data for. My rationale for using NASA's MERA-2 atmospheric reanalysis data was, one, it was the closest thing that I could find to historical dust surface concentration data for Grenada, and two, to the best of my knowledge, there have not been any dust surface concentration measurements previously conducted in Grenada for any extended period of time before. My rationale for using daily mean visibility data was 1. Poor visibility is caused by tiny particles and gases in the air, and 2. On bad air pollution days, I assumed that air pollution causes poor visibility in Grenada. And finally, the third reason is that if there was poor visibility and a concerning level of dust surface mass concentration occurring on a particular day in Grenada, I believe it is very likely that a Saharan dust day occurred. The methodology that I use goes as follows. Step 1. Days with a dust mass surface concentration of 15 micrograms per meter cubed or greater were flagged as potential Saharan dust days in Grenada. The reason why I included this step was that the WHO's 24-hour guideline value for PM2.5 is also 15 micrograms per meter cubed. Step 2. Days that satisfied Step 1 while also having a daily mean visibility of 15 kilometers or less were classified as very likely Saharan dust days. The reason why I included this step was that days with a mean visibility of 15 kilometers or less were classified as Saharan dust days previously by the Trinidadian Meteorological Office. Alright, with that out of the way, let's get to the results. The number of Saharan dust days in a given month during my study period ranged from 0 to 14. After calculating the average quantity of Saharan dust days for each month, I found there to be a trend of more such dust days from March to July and a trend of less such dust days from August to February. As you can see, December was the month with the minimum average amount of dust days, and June was the month with the maximum average amount of dust days to occur in Grenada. Next, here's a comparison of the historical monthly mean dust mass concentration box plot in Barbados compared with a box plot that I made displaying MER2 daily mean dust mass concentrations grouped by month from 2000 to 2022. When comparing the meteorological variables with the MER2 dust surface mass concentration on a daily basis, I found no correlation with relative humidity, a moderate correlation with visibility, and a weak correlation with temperature. When using my updated method for identifying Saharan dust days in Grenada, Purple Air measured daily mean PM2.5 was more than 3 times higher on Saharan dust days compared to non-dust days in 2020. In contrast, when using my thesis method, Purple Air measured daily mean PM2.5 was only more than 2 times higher on dust days compared to non-dust days in 2020. When comparing the Purple Air PM2.5 data that I collected during my thesis to the MER2 derived PM2.5 data, I found a strong correlation with Pearson correlation coefficients of 0.71. While there was diversity in the strategies used to combat the spread of COVID-19 around the world, nearly all countries implemented some form of restrictions to reduce the person-to-person spread of disease. Consistent among most of these lockdown measures were restrictions on transportation and industrial activities, 2 main sources of ambient air pollution. Thus, the pandemic provided me the opportunity to examine how abrupt changes in human activity from these COVID-19 restrictions impacted outdoor air quality in Grenada. The beginning of the pandemic in Grenada was characterized by the implementation of various public health measures via the Emergency Powers Act. And in this study, I did my best to characterize these public health measures in the form of variables. To quickly review, here are the COVID-19 restrictions variables that I created. In an effort to try and estimate the impact of COVID-19 restrictions on outdoor concentrations of PM2.5, I used the statistical method known as multiple regression. Put simply, multiple regression is a method used to examine how multiple predictor variables, which can be continuous or categorical, relate to a single outcome variable. Our most noteworthy finding from this section was that the implementation of COVID-19 public health measures was associated with an estimated 27% decrease in ambient PM2.5. This result was achieved while adjusting for meteorological variables and the occurrence of Saharan dust days. For context, adjusting just means accounting for the influence of predictor variables other than COVID-19 public health measures so that I can best isolate the specific effect that these measures have on daily mean PM2.5 values. My finding of a 27% reduction is consistent with those found in other countries as shown in this 2020 review paper by Gosh and Gosh. The study reviewed 15 studies examining air quality during COVID-19 lockdowns across 15 different countries, and the authors reported an average decrease in PM2.5 of approximately 27%, comparing pre-lockdown to lockdown period concentrations. The final major result that I want to discuss is that I failed to detect any statistically significant associations between specific public health measures and daily mean PM2.5 in Grenada. For context, a study examining the impact of COVID-19 related lockdown measures on air quality across 162 countries found that the implementation of curfews resulted in decreased PM 2.5. In major Saudi Arabian cities, during periods with social gathering limits in effect, reductions in NO2 and CO and marginal increases in PM10 concentrations were all documented. No studies could be identified that examined the impacts of changes in commercial airplane flights due to COVID-19 and surrounding ambient air quality. However, I did find 2 studies that examined changes in boating/shipping traffic activity during COVID-19 and ambient air pollution emissions. In these 2 studies, the emissions of air pollutants such as SO2 when associated with the COVID-19 lockdowns were either unchanged or marginally increased compared to non-lockdown period concentrations. Among the most significant strengths of this project was the collection of ambient PM 2.5 data in Grenada for nearly a year. That allowed for the characterization of day-to-day variations, time-of-day variations, and the assessment of Saharan desert dust impacts on PM 2.5. While day-to-day variations in ambient particulate matter have been monitored on the Caribbean island of Guadeloupe, it has never before been studied in Grenada. Similarly, Trinidad and Tobago are the only other Caribbean islands that have had time-of-day variations in PM 2.5 assessed before. However, these hourly measures were from a small sample size, which is not as exhaustive as the hourly PM 2.5 measurements taken across 157 days for my box plot comparison. As well, Guadeloupe appears to be the only other Caribbean island that has had the impacts of Saharan dust days on day-to-day ambient PM 2.5 concentrations examined. Altogether, my study provides initial ambient PM 2.5 exposure data to justify future studies in Grenada. Another strength of this project was demonstrating that all days of high ambient PM 2.5 were due to Saharan desert dust episodes. This yields an important finding that natural sources of ambient air pollution appear to be impacting outdoor air quality in Grenada much more than local anthropogenic sources. In addition, my study adds to the historical record of dust transport to the southern Caribbean region. This is important because in the last decade, it appears as though seasonal patterns of dust transport to the Caribbean have been more erratic, potentially due to anthropogenic-induced climate change. My study also improved upon existing methods of identifying Saharan dust days in the Caribbean region. That is, when collecting physical samples of dust particles is not an option. The method I used for my thesis, and my recently updated method of identifying Saharan dust days, can be replicated with relative ease, so long as daily visibility measures can be obtained and internet access is available to utilize online tools like NASA's Mirror-2 aerosol data. A final strength of this project is that it is among the first to quantify the impacts of COVID-19 related public health measures on ambient air quality in the Caribbean region. Measures of ambient PM 2.5 in Grenada throughout COVID-19 suggest that human activities are not driving major changes in ambient air pollution on the islands. However, further collection of ambient PM 2.5 data on the islands is required to confirm this hypothesis. As well, this project is among the first to examine the impacts of specific COVID-19 related public health measures in ambient PM 2.5. Over the course of my study period, several of the Purple Air PA2 SD monitors stopped working and required repair. I suspect that these monitor breakdowns are due to the combination of high humidity and sea salt spray exposures. For context, Grenada has relative humidity levels routinely above 70%. As well, 4 of the monitor locations for this study were close to a coastline, indicating the potential for consistent exposure to sea salt spray. It's possible that these 2 factors may have impacted internal parts of the monitors that malfunctioned, such as corroding the power cord or impacting the laser channels that are responsible for particle measurements. In future work, I recommend pairing a reference grade monitor with one of the low-cost monitors to compare measures of ambient PM 2.5. Some reference grade monitors have drying or heating facilities that would be beneficial since they mitigate the impacts of high relative humidity by removing all liquids from the particles being measured. This is important because the presence of water on the particles plays no part in the adverse health effects particulate matter causes upon exposure. The second major limitation of my project stems from a lack of available historical data to compare with the PM2.5 data that I collected in 2020. The lack of historical data meant that there was a lack of knowledge of the year-to-year variability in PM2.5 concentrations in Grenada. This made it difficult for me to contextualize the PM2.5 data collected in 2020, especially so for the measurements taken during the COVID-19 pandemic. To remedy this concern, I recommend continued long-term monitoring of air pollution on the island. Another major limitation of my project was that while measurements of ambient PM2.5 to quantify the impacts of COVID-19 on pollution changes was sufficient, it may not have been optimal. Since particles can travel further than gaseous pollutants, measures of fine particulate matter include both local and regional sources of pollution. Therefore, measurements of ambient nitrogen dioxide, a good indicator of traffic pollution, may have been more helpful in quantifying the impacts of COVID restrictions on ambient air quality in Grenada. This is why I also recommend the use of NO2 monitors in future studies in Grenada, as it will likely be less impacted by regional sources of air pollution. The final limitation I want to discuss is that our findings are based on the use of low-cost monitors as opposed to higher accuracy and higher cost reference grade monitors. For this study, we lacked the funding to purchase and utilize reference grade monitors. As aptly described by Grenada, correction measures are usually advised to adjust data from sensors to improve their accuracy so that they are more comparable to regulatory monitors. Basically, to best utilize lower-cost air quality devices, it's best to pair them with a reference grade monitor and calculate an equation that best adjusts your lower-cost monitor data to align with that of higher accuracy reference grade monitor data. This is especially important given the possible measurement bias of PM2.5 by purple air monitors during Saharan Dust events. Unfortunately, we did not have the funding to perform such a co-location study. To cap this section off, my final recommendation is to explore creating a land use regression model for the St. George's area, Grenada's capital city. LUR models can be advantageous for characterizing air pollution concentration variability on small spatial scales. For St. George's, installing 20 to 30 high-grade monitors for 2-week periods throughout multiple seasons of a given year should satisfy the data requirements for constructing a proper LUR surface model. This land use regression model can be constructed using ambient measurements of air pollutants such as NO2, PM2.5, or ultrafine particles. In the past, there has been little monitoring of air pollution in the Caribbean. This has changed somewhat. As of April 2024, there are air pollution monitors, most of them being purple air, in Barbados, British Virgin Islands, Cayman Islands, Grenada, Jamaica, Montserrat, Puerto Rico, Trinidad and Tobago, and US Virgin Islands. Data from my preliminary air monitoring study in Grenada suggests that ambient PM2.5 concentrations on this island are lower than in most other countries. The impacts of episodic Saharan dust plumes were significant and responsible for nearly all days when relatively high ambient air pollution concentrations were recorded. My study also revealed that the application of public health restrictions by the government to curtail the spread of COVID-19 were associated with reduced concentrations of PM2.5 by approximately 27%. At the beginning of this video, I posed the following question: what is the value of measuring the quality of our air? By determining the concentration of harmful substances in the air, I propose that systematic air quality monitoring is immensely valuable in guiding public authorities to implement air pollution reduction measures when required and provide recommendations to limit people's exposure during high pollution events. By staying informed, I believe that public health authorities can take proactive steps to mitigate the health risks and reduce the associated economic costs of air pollution exposure. With that said, thank you so much for watching, and bye for now. Yeah, so without further ado, here's the start of my air quality monitor building journey with a Raspberry Pi.